Hello, my name is Allen-Perales, and I'm going to talk about volume above, distance below, with and without boundary, and applications. This is a follow-up talk to Brian Allen's talk. I would like to thank the organizers for giving me the opportunity to speak in this virtual workshop on reaching scalar curvature in honor of Misha Gromov. My talk is going to be as follows. I will talk about results and applications. Then I will describe a little bit about intrinsic flat convergence. I will give some history about why we are proving these results. And then I'm going to give a sketch of the proofs of our main theorems. So let's start with the first part, the results and applications. In this theorem, so we have this theorem, which was proven by Allen, myself, and Sormani. We have a fixed manifold M, which is closed. So that means that it's compact and it does not have a boundary and it's oriented. So we require to have a smooth Riemannian tensor G0 on M and a sequence of continuous Riemannian tensors Gj on M. So then we form the Riemannian manifolds M0 and the Riemannian manifolds Mj. We require that G0 is less or equal than Gj, a uniform diameter bound, and the convergence of the volumes. So here we have this convergence of volumes. And under these conditions, we can prove that our sequence of manifolds converges to M0 in intrinsic flat sense, and that the volume is preserved. This V stands for volume is preserved, which we of course have because of our hypothesis, but it's very good to write it here because this does not happen in general using intrinsic flat distance. The remarks of this theorem are as follows. The inequality on the tensors G0 less or equal than Gj can actually be thought of as an inequality of the distance functions with respect to the Riemannian tensors. So G0 or M0 is the points in M0 will have a smaller distance than the points in Mj. Then this inequality of the tensors also implies that the volume of G0 is actually less or equal than the volume of Mj. So this volume convergence is actually a monotone volume convergence. It's and the second, well, the third thing that I want to mention is that if we also have equality of the volumes, then the Riemannian tensors should be the same. So this is a stability theorem in which we are relaxing the condition volume of G0 equals volume of Gj. And the last remark that I want to make is that the inequality G0 less or equal than Gj can be replaced by this new inequality. So 1 minus 1 over 2 over J, G0 should be less or equal than Gj. So we are also relaxing this condition in our theorem. Now, let me give you an example of what type of sequences we are considering. So here M0 is the manifold inside, the pink manifold, and we have depicted M1, M2, and M3. So these are gray manifolds. So it's easy to see that the diameters are uniformly bounded, that the volumes of M1, M2, and M3 are bigger than the volumes of M0, and also that the distances are bigger in M1, M2, and M3. So they satisfy all the conditions of our theorem. And also this sequence won't have a Gromov-Hausdorff limit, nor C0 convergence of the distance functions to M0. So let's move on. This second theorem is follows very easily from the proof of theorem 1 plus some other things. And here what we have is a manifold, fixed manifold M as before, and it is compact. So that means we are allowing to have boundary. And we required the interior of M to be totally convex with respect to G0. Furthermore, since we have boundary, we will require a uniform bound of this type. So volume of boundary Mj should be less or equal than A, and plus the other conditions that we already stated in theorem 1. Under these conditions, we will still have intrinsic flat convergence to M0. The next theorem, so this next theorem is just with Allen, and this paper only deals with manifolds with boundary. So here again, we have M fixed manifold that is compact with boundary and oriented. And what we require instead of having a totally convex interior with respect to G0 is that the M-1/2 norm of Gj minus G0 restricted to the boundary of M to converge to 0. So under this hypothesis, we also have intrinsic flat convergence to M0. And the remark is that in this theorem, we have a strict inequality, G0 less than Gj, but this also can be replaced by this inequality. Okay, so we start with a strict inequality because we have to prove a technical theorem, but after we prove this, as a corollary, we can relax the condition on the tensors. And finally, my next main theorem, what we do is we drop the condition of the volume convergence and we replace it by the M/2 norm of Gj minus G0 converging to 0, and a uniform diameter bound. And a uniform volume bound of this type. So we want the volume of boundary Mj to be less or equal than A. So under these conditions, we have intrinsic flat convergence to M0, and we also have volume convergence as well. So these are the main theorems that I wanted to present, and now I'm going to talk about the applications. This is an application of the theorems of manifolds with boundary. And so let me start with the rigidity statement of the positive mass theorem. So it says that any complete asymptotically flat Riemannian manifold M with a non-negative scalar curvature and ADM mass equal to 0 should be Euclidean space. So then, what Allen-Perales-Sormani and many other people ask themselves is, what happens if we instead consider a sequence Mj, and we require that the mass is converging to 0. Because of the rigidity case of the positive mass theorem, we expect that this sequence converges to Euclidean space. And what Allen-Perales and Sormani were able to prove for a class of manifolds that are asymptotically flat, complete, with non-negative scalar curvature, so this class, Gn, they were able to prove convergence of this type. So what we are going to do is we have our manifold Mj, and we intersect it with a cylinder in Euclidean space of dimension n+1. So that region omega j looks like in this picture. So this is the part in which I intersect with a big cylinder, well, with a cylinder of radius r. And then this type of regions will converge to a ball in Euclidean space. So these conditions are zero. R0 means that outside of the ball of radius R0, we have nice asymptotics. The nice asymptotics are given by gamma and other conditions. And then inside the ball of radius R0, we have this t, and this t is related to this depth, how far we can go, or how low we can go. And this alpha is asymptotics in the case that the dimension equals 4 or 5. So let me move on. And, oh, okay. So there are more results addressing the stability of the positive mass theorem or the space-time positive mass theorem by Lee-Sormani, Stavros-Sormani, LeFloch-Sormani, Bryden-Curry, and Sormani. Our next application of our theorems, so this is an application of theorem 1, where the manifolds do not have boundary, is the following. So Shane and Yao, Gromov and Lawson proved that an m-dimensional torus with a Riemannian metric such that the scalar curvature is non-negative should be isometric to a flat torus. So then one wonders what happens if we relax the condition on the non-negative scalar curvature. So now we will have a sequence of tori, MJM, where the scalar curvature is negative, but it will converge to 0. And we expect this sequence to converge to a flat torus. So this is what we prove. We prove it for certain class. This class is a model after the class of Wang Li and Wang Li-Sormani to prove the stability of the positive mass theorem with respect to flat distance or intrinsic flat distance. So the way to prove these two applications is the following: with the conditions imposed in the class MDA or in the class G and R0 gamma d alpha, one is able to prove diameter bounds that volume converges. That is, and also that the tensors satisfy the inequality G0 less or equal than Gj. Okay, so these terms are proven in this way. And just to finish, let me tell you that there are more results addressing the stability of tori for different classes of tori. So in particular, Allen, Hernandez, Vasquez, Paris, Pine, and Wang show the stability of tori for warped tori in 3 dimensions. And this is some of the papers that I mentioned in the previous slides.